In this tutorial, we are going to see gate question asked in CSE department in the year 2025. It's a 2-mark question. Okay. The question is, 3 floating point numbers, namely X, Y, and Z, are stored in 3 registers, which are RX, RY, and RZ. And it is stored in IEEE 754 single precision format. And the value in terms of hexadecimal are given as Rx is given here, Ry is given here, and Rz. The question is, some expressions are given, something like 4 times x plus y plus z is equal to 0. We need to verify by substituting the values of this x, y, and z in this equation, and we need to ensure that it is going to be 0. If it is 0, then the expression is said to be correct. Like that, we need to verify all 4 options, and we need to identify what are the options are correct. Okay. In order to solve this problem, we need to be familiar with IEEE 754 single precision format. It's a 32-bit representation in terms of binary. Here the first digit represents sign. It has 2 possible values. If when it is 0, it's a positive number. When it is 1, it's a negative number. Coming to the next set of bits, it represents exponent. It is not just a normal exponent, it is biased exponents. It represents the power of 2. Normally we speak about power of 10, 10 power 3, 10 power 2 and all. Because it's a binary representation, it is power of 2. And it can represent both positive as well as negative values. And it is a biased number. Biased in the sense, we are going to add some additional value with the original one. Here in this case, in IEEE 754 single precision format, we add 127 as a biased value. If original value of exponent is 3 means, we add 127 with this and we store the binary equivalent of 130 into this place. Instead of storing 3, we store 127 plus 3, it is equal to 130 we store in this particular biased exponent part. And there are reasons behind this. If you go for biased representation, then we can perform floating point addition, floating point subtraction. All those things will be much easy if we go for this biased exponent representation. The next one, mantissa part. Mantissa is nothing but the fractional part which follows after the binary point. So it comes here after the binary point, it comes. And it has a leading one which is not stored anywhere. By default, a 1 comes here, followed by the binary point, after which we write the mantissa, which is nothing but the fraction part which follows here. So in general, you want to calculate the value of this particular hexadecimal representation, or I can say the complete binary representation you want to convert into equivalent decimal means the sign comes here. That means -1 whole power sign, 1 followed by binary point. After the binary point, this mantissa part comes here. The whole thing is multiplied by 2 power the biased exponent minus 127. Nothing but the actual exponent value. We get it after subtracting 127. So this is the whole format of IEEE 754. Now let us try to convert the given values. There are 3 values given to us. One is Rx, the second one is Ry, third one is Rz. We start with Rx. We try to expand and substitute in the IEEE 754 representation. The first digit, hexadecimal digit is C. C means 1100, right? 12 in terms of decimal it is 12. If we expand in binary it is 1100. The next digit is 1. 1 means 0001. You see here 0001 comes. Again, next digit 1. 1 means again 0001. The rest of the digits are 0. So you simply keep zeros afterwards. Is the idea clear? So we substitute this Rx value, just expanding into each digit into 4-bit binary equivalent and substitute here. Now let us try to find the value in terms of decimal. For that, first we calculate the value of actual exponent. Here we see biased exponent. We must convert into actual exponent. For that, what we do? We convert this biased exponent in terms of binary into decimal. If you consider here, this digit represents 128. This particular position 2, right? So 128 plus 2, it becomes 130. And subtracting 127, it's a bias value. If you subtract, you get 3. 3 is nothing but the actual exponent, which has the base of 2. Now, substituting the sign here in the standard representation, it is power. So minus 1 whole power 1 means it becomes minus. Multiplying this minus 1, this becomes minus, right? And this 1, which leads your normalized representation of your floating point number, it comes by default. It is nowhere mentioned here. Only the fractional part or mantissa part, what we observe here, follows the binary point. Because it is 0010 followed by a number of zeros, we just keep it here. Now, because it has minus 1 whole power 1, it becomes minus 1. So multiplying with minus 1, it becomes a negative number, and the fractional part follows, followed by 2 power the actual exponent. Now this 2 power 3 is nothing but number of position we want to shift rightwards. Because it's a positive 1, we shift in the right direction. Because it is 3, if I shift in the right direction by 3 position, it becomes 1001. Right, followed by binary point, then 0. After binary point, if you have 0, it doesn't have any value, it's going to be 0 only. So 1001, if you convert into decimal, it becomes 9. We keep the minus sign as such. So it becomes minus 9 base 10. So the value of x in terms of decimal is minus 9. The first one we have applied. Now we are going to adapt the same thing for the second floating point number also. It is given like this: 40C0 followed by 4 zeros. Now also you expand it to 4 binary digits for each hexadecimal digit. So 4 means 0100. In the same way, followed by 0, followed by C means 12, then followed by 0, and so on. So once you substitute all this, we need to calculate as usual the actual exponent value. You convert this biased exponent in terms of binary into decimal. It gives you the value of 129. Subtracting 127, we get the actual value of exponent as 2. So it's nothing but 2 power. Now minus 1, the sign part, it is 0. You substitute the fractional part here, and it is 2 power 2. 2 power 2 means we shift the binary point by 2 positions. It becomes 110. And it's a positive number because minus 1 whole power 0. Anything power 0 is equal to 1, a positive number, right? Multiplying by 1, you get the same value. It is 110 is nothing but 6 base 10. So y value is plus 6. Adapt the same procedure for RZ also. So it is 4 means 0100. Again 1 means 0001. You adapt the same procedure. You apply in this particular procedure what we have followed here. We get the value of y as plus 12. Now let us come to the expressions given in the question. There are 4 options given. We need to verify one after the other. We have calculated the value of x as minus 9, y as plus 6, z as plus 2. The first option, if you see, 4 times x plus y plus z. So 4 times the value of x is minus 9. You substitute here. Add with y. Y is plus 6. So minus 9 plus 6. The whole thing you have to add with z. That means plus 12. So minus 9 plus 6 gives you minus 3. 4 times minus 3 will becomes minus 12. Adding plus 12 will give you the value of 0. So the first option, given option, is true. The second expression, if you consider, This is our B, option B, 2y minus z. So 2 times y means 2 times 6, it is equal to 12. Minus z means already z value we know 12. So subtracting 12, it becomes 0. So this expression is also true. The third expression, 4x plus 3z is equal to 0. So 4 times x means 4 times 9. It becomes minus 36. And it is 3 times z means 3 times plus 12. So it is also plus 36. So minus 36 plus 36 gives you the value of 0. So this expression is also true. Finally, the fourth one, x plus y plus z is equal to 0. Let us verify. Minus 9 plus 6. It is minus 3. Minus 3 plus 12 is plus 9. So it is not equal to 0. In the expression, it is given 0. So this is not true. So the correct options are option A, B, and C.